Hi, in this video I'm going to discuss oxidation and reduction of alcohols. So the first thing I want to mention before I go into some of the reagents that are used for oxidation and reduction and their mechanisms is which alcohols can and cannot be oxidized. So primary alcohol can be oxidized. Secondary alcohols can be oxidized because each of them you have hydrogens that allow you to oxidize the alcohol. Once you get to a tertiary, though, this cannot be oxidized. There's no hydrogen that is in a position where you can oxidize that oxygen. And you'll see once we get into the oxidation reactions why that hydrogen is needed to be there for the oxidation to take place. So the first reactions I'm going to start with are actually reduction. So reductions of ketones, aldehydes, carboxylic acids, esters into alcohols. So the first reagent I'm going to discuss is sodium borohydride, or NaBH4. This can reduce ketones and aldehydes. The mechanism is I've got my ketone right there. And the mechanism is going to be the same with an aldehyde. NaBH4 is a source of hydride. Right? Generally, a hydride ion doesn't act as a nucleophile, right? Just a base. But with borohydride, you got your sodium plus, and then BH4 minus. So one of these hydrogens is going to come in and kick the electrons from the double bond up to the oxygen. Now quench with water. And you get your final product. So pretty simple mechanism for the NaBH4, or sodium borohydride. A second reactant is lithium aluminum hydride. It's often written as LAH. It proceeds with similar mechanism to the sodium borohydride. What makes LAH different is that it is stronger. So it is able to reduce carboxylic acids and esters, whereas sodium borohydride can't. So the mechanism for that, so I've got LAH now. This is going to be the mechanism first for an ester and then for a carboxylic acid. So for an ester, I have my ester, right? LAH, think of it again as just the source of H minus. Will come in and attack the carbonyl. Next, the electrons are going to come back down to form a double bond, right, that's a hydrogen now, and kick off the methoxy group. So now I'm left with an aldehyde. So I react with LAH again. So I have to have two equivalents here. Next, add in water. The oxygen will be protonated, and I get a primary alcohol. So that's the mechanism of LAH reacting with an ester. The mechanism with a carboxylic acid is a little bit different. So here I've got my carboxylic acid, and I'm going to react it again with the LAH. What happens here is this is going to look a little different. I have my aluminum, 2 hydrogens over there, another hydrogen down here. Right, in this first step, the LAH deprotonated the hydrogen. So I only have an O- down there now. Okay. And in the process of the deprotonation with the LAH, we lost hydrogen gas. Right? That's the reason we only have 3 hydrogens on the aluminum now. So we lost that hydrogen gas, and we have some coordination going on here. Right? Negative dipole on the oxygen up here is coordinating with the positive aluminum. It's a metal. Right? And then we have the oxygen down here, basically hydrogen bonding with one of the hydrogens. So now I'm going to draw in the arrows. I form a bond between the oxygen and the aluminum. And then I'm going to move the electrons from the aluminum hydrogen bond down here. Okay. So the coordination here, the one change from what I wrote is it's coordinated there. So the bond is going to form between the hydrogen and the carbon, not the hydrogen and the oxygen. Okay, so these are the arrows we've got going on. Electrons moving to form a bond between the oxygen and the aluminum, and the electrons moving from the aluminum hydrogen bond to form now a carbon hydrogen bond. So now we have the oxygen with the aluminum, so ALH2 now, it's lost another hydrogen. We have the new carbon hydrogen bond there, and then an O- still. Electrons are going to move down here and kick off that oxygen with the aluminum to now give an aldehyde. It's then going to proceed. All right, we got LAH, so another hydride ion. It'll proceed with the same mechanism I showed with the aldehyde to form a primary alcohol again. Here we go. Quench with water. And you've got your primary alcohol. I know that mechanism is a little bit confusing, but that's how you have LAH react with a carboxylic acid to form a primary alcohol. The last reducing agent that can be used is one you're probably familiar with because it's been used before for reducing, but for reducing alkenes and alkynes. And that is hydrogen with a palladium, platinum, nickel catalyst. Right. There's one issue with the hydrogen though. Like, it's perfectly capable of being used, but say I have a compound like this. If I react it with LAH or sodium borohydride, I'll get that. If I react it with H2 with, palladium on carbon catalyst, not only will I reduce the ketone to an alcohol, I'll also reduce the carbon-to-carbon double bond. So it's not selective. So you can use hydrogenation to reduce a ketone to an alcohol, but if there's other double bonds in your compound, it's also going to reduce those. So it's not selective to only the ketone, whereas LAH and NABH4 are. All right, so next I'm going to move on to oxidation. So oxidizing agents, going from an alcohol into a carbonyl, whether that's a ketone, carboxylic acid, aldehyde. It'll depend on what reagent you're using for the oxidation. And the oxidation mechanisms are very complex. Often oxidation is done with chromic acid or PCC. And chromic acid is the stronger of the two. So kind of like LAH is stronger than NABH4, chromic acid is stronger than PCC. Both of these are chromates, right? PCC is a chromate, it's just the abbreviation for the longer name of it. Now, chromic acid will often be written as CrO3. You may also see it as Cr2O7, right? That's going to be chromic acid. It oxidizes primary alcohols into carboxylic acids. So if I have that as my reactant, if I react it with chromic acid, I'm going to get just make sure I count my carbons right. 1, 2, 3. That's why you count your carbons. Yep, that's why you always count your carbons. Make sure you don't mess up the number of them. So that's what happens with chromate. PCC, on the other hand, oxidizes primary alcohols to aldehydes. It is not able to oxidize them to carboxylic acids. Both chromic acid and PCC oxidize secondary alcohols to ketones. Right, so if you're doing a synthesis and you need to get to a ketone, you can use either of them if it's a 2' alcohol. But if you're doing a synthesis and you're trying to get a carboxylic acid from a primary alcohol, you need to use chromic acid, not PCC. So to review, I'm just going to give the reducing agents and oxidizing agents that we have gone over. So reducing agents, we got LAH, we got sodium borohydride, and we got H2 with a palladium, nickel, platinum catalyst. Usually I've seen it with palladium, but nickel and platinum can be used as well. Then oxidizing agents, you've got chromic acid and PCC as the two major ones. There are others, especially with green chemistry. Any really chromate compound is very toxic and very reactive, so it's better not to use them if you don't have to. So there's other oxidizing agents you may come across, bleach with acetic acid. Oops, did that wrong. Right, bleach with acetic acid is one you may come across, but again, these are the two major ones. And when you're taking a test or doing homework and being green doesn't matter, and all you have to do is just write out what the synthesis would be, chromic acid, PCC are great reagents to use for synthesis.